In this video, we're going to look at God's design of mathematics, and we're going to consider how we do mathematics. We do mathematics by discovering and or applying principles and theorems that God has built into the universe. And here's some of the features. We may apply different theorems to a problem and get the same answer. Humans discover and apply the theorems. Theorems discovered will work consistently and can be used in combination because God sustains the principles in theorems, and God has built amazing relationships into mathematics. So we're going to consider, like, say, a simple algebra problem. Think, let's say, if you want to solve for x in this problem, you could do this a lot of different ways. We could put the coefficients of x together on the left and on the right, then move the 4x to the left, and then divide by 2, and we get our answer 15. Now, we could have done this in many different ways. We could have applied different theorems, did things in a different order. So, for example, let's go back to it again. But this time, let's start with dividing by 4. If we divide by 4, we get these messy fractions. Again, probably not a good way to do this problem. But again, if we combine the x's on the left and the coefficients of x on the right, move the negative x to the left, multiply both sides by a half, and we still get x equals 15. Now, this problem could have been done in many different ways, and we could have done different orders, but we would have gotten the same answers as long as we apply the theorems properly. This is one piece of evidence that mathematics is designed. It shouldn't be the case that if you solve a problem in two different ways that you get the same answer if it was created, that if humans were creating it. If humans were creating it, there wouldn't be that underlying consistency there. Again, we're going to later go to more difficult problems to really see how this works. Now, God has created the principles that drive mathematics, and he sustains them. He keeps these principles and theorems going. People discover and apply the principles that God has created. Humans can't invent or design theorems. For example, we know that if you take x plus y squared, that's equal to x squared, y squared. Or if you have x plus y squared, if you want to FOIL it, you get x squared plus 2xy plus y squared. Now, if you tried to impose your own rules on this, nothing would work. For example, let's say if you wanted to define xy squared equal 2xy, then theorems wouldn't work. You couldn't put anything together. You just can't do it this way. Or no matter how much you try, and a lot of first-year algebra students will try to do this. They'll do x plus y quantity squared is equal x squared plus y squared. They'll try to distribute the two, the way you do if it was x times y, but you can't do that. So we can't define the rules. We have to go by whatever rules that have been built into mathematics. And these are rules that God has built into it. Now, humans can create the symbols for math. We could have used different symbols, for example, for plus. For plus, we usually use this cross-like symbol. Now, plus could have instead been represented by this symbol. There'd be nothing wrong with that as long as you defined it that way and used it consistently. That could be used for plus. Or for equal, we use this. Now, we could just have easily have picked another symbol like this odd symbol here. And then instead of saying 2 plus 2 is 4, written this way, we could have written it with our new symbols here. And that would be perfectly legitimate as long as we define them that way. And as long as we use them consistently. But we can't change the way math works. We can't say that 2 plus 2 is 5, whether we write them in the symbols we're used to or in these new symbols. It just won't work. Again, humans discover and apply theorems, that God has created. Humans do create the symbols for mathematics. Humans name things in mathematics. Often theorems will come out and they'll give them different names and sometimes arbitrary names. Sometimes one person will name them one way, another person will name them another way. That's all legitimate. And we can even create the format in which math is done. You could write math sideways from right to left, uh, diagonally across the paper. The format is something humans can create. So once again, let's consider something else, like say a right triangle. We have this right triangle, and we know the relationships, Pythagorean's theorem, and the right angle laws. Uh, Cos of phi is the adjacent over the hypotenuse. Sine of phi is the opposite over hypotenuse. Tangent is opposite over adjacent. And so these are relationships that have been discovered and they work consistently over and over again. And they'll always work. It doesn't matter what equations you use uh, in which you apply these theorems, it'll always work. Like, for example, we could find C by using Pythagorean's theorem, or we could first find phi given A and B, and then use cos to find C, or we could find phi and use sine to find C. So there are many different ways, even on a simple problem like this, that we can solve it, and we don't have to do it in any particular order as long as we use the rules that have been discovered. Now, many other relationships exist that aren't even noted here. There are still some probably to be discovered. And these relationships were designed into the triangle. People can't invent new relationships. We can only discover the relationships that God has designed in the triangle. For example, we can't say that C equal A times B in a right triangle, or that B is equal to some constant times A divided by C. These equations would probably make things much simpler, but they just don't work. They haven't been derived, they not discovered, and they won't work. We can only use relationships that God has built into the universe. Now, once again, the names and symbols are not fixed. We can name them anything we like. Instead of sine, cosine, tangent, we could have used, say, Russian names. We could have used Igor, Natasha, and Boris, as long as the functions themselves still acted like trig functions. So in that case, we would have said Natasha, which is the similar to cosine is of phi is A over C. Igor, same as sine, is B over C. And Boris, same as tangent, is B over A. These would be perfectly legitimate as long as the functions themselves act the way the function should. For example, if we have this relationship, Natasha should act like the cosine function. Igor should act like the sine function, and Boris like the tangent function. So once again, humans create symbols for math, and we can name things in math, much like Adam was permitted to name the animals. Remember, God brought the animals in front of Adam. He could name them. Now, but he didn't create the animals, and he didn't create mathematics. And also, to some extent, we can determine how math is arranged and presented. But the principles, the theorems, they were created and sustained by God. Humans can only discover these principles, not change or create new ones. Now, something really interesting, consider the factorials. These are used a lot in statistics, combinatorics, etc. Factorial, like say 4 factorials, 4 times 3 times 2 times 1. 7 factorials, 7 times 6 times 5 times 4 times 3 times 2 times 1. And in general, R factorial, as long as R is a positive integer, is R times R minus 1 times R minus 2, go all the way down to 1. Again, these are really important relationships used every day millions and maybe billions of times to calculate things. It calculates, say, permutations or combinations, would use these equations. Now, as you're calculating these numbers, sometimes you'll end up with, say, 0 factorial. For example, in those equations, you sometimes end up with 6 minus 6 factorial, which is 0 factorial, or 9 minus 9 factorial, which is 0 factorial. So, which should be assigned to 0 in this case? Recall that 0 to the x is 0 as long as x does not approach infinity. The square root is 0, 0. 0 times 0 is 0. So should we set 0 factorial to 0? So what value should be assigned to 0 factorial? Remember 3 factorials, 3 times 2 times 1, which is 6. 2 factorials, 2 times 1, which is 2. 1 factorial is 1. So which should 0 factorial be? Now, if you look at the pattern here, it seems logical. 0 factorial should be 0. Consider n factorial. Now, we could take an n out of that, and that would be n times n minus 1 factorial. We get something like this. And now let's set n equal to 1 and see what happens. So if we set n equal to 1, we get 1 factorial is equal to 1 times 1 minus 1 factorial. Now on the left, we know that 1 factorial is 1. And then on the right, we're going to have 1 times 0 factorial. So what does this mean? If we, 1 times 0 factorial just leaves us 0 factorial. So this ends up being 0 factorial is equal to 1. Not what we would have guessed, because 1 factorial is 1. Why would 0 factorial also be 1? But when we look at this, this is what's derived. So 0 factorial equal 1 works. In fact, if you try it in any of those combinatoric or permutation equations, combinations, permutations, it'll always work. No other value for 0 factorial will work. If we tried to assign 0 factorial to be 0, everything would blow up. Nothing would work. So this is another case here that shows that God has designed the mathematics. Humans can't assign values even if they seem logical. But if we derive them from the existing formulas, we'll get something that works, and it'll always work. Now, the other question, what if the principles did not always work? What if mathematical principles work differently each time? We solved our original example in 2 different ways, got the same answer. What if we would get different answers? Of course, there would be chaos. We couldn't do math at all. We just automatically assume that everything's going to work nicely together, that as long as we apply the theorems properly and build on those theorems, that everything's going to be fine. And again, it works consistently because God has designed it that way. If we were just creating the math, there's no way we could figure out all the possibilities, all the combinations, and the way things could always work. But since it has been designed by God, everything works together. Another thing that's important is that we build theorems upon theorems. Think of the way we use axioms to prove theorems, and we're building on top of those theorems hundreds and thousands of other theorems. Every day in mathematics, we're using theorems that have been built on top of other theorems, on top of other theorems, on top of other theorems. It goes on and on and on. We have like millions and billions of theorems all built on each other. And we can do this because we know once we've established a theorem, we can use it as it is, and we can even use it to build other theorems because God has designed it that way, and he sustains it so that it can work. Hundreds of theorems lie behind calculus theorems. Many theorems are used to prove other calculus theorems. If any one of the other underlying theorems fails, calculus would be worthless. We couldn't do math at all. Think of all the theorems are used to solve a basic calculus problem. And again, this I see this picture is a little bit fuzzy. I'll kind of rush through this kind of quickly so you don't have to look at this fuzzy picture. But let's say you did this integral here. Let's say if you wanted to solve this, first you would apply the half angle and double angle formulas. Then you would separate the integrals. Then on the right, you apply integration by parts. Then you would actually integrate the sign and then multiply through by 0.5. And then our final answer is this right here, 1/2 x squared minus 1/4 x sine 2x minus 1/8 cos 2x. And you could check the answer by taking the derivative. So you could apply a whole bunch of other theorems. Take the derivative, then combine things, factor out an x, and then use the half angle, double angle formulas to get back to your original. Again, I wanted to flip through that quickly because it's a little bit fuzzy. So again, notice what we did in this. First, we used trig identities, like the half angle, double angle formulas. We used the fact that the integral of a sum is the sum of the integrals. We used the rules having to do with a constant times an integral. We used a power rule for integrals. We used the rules related to integration of trig functions. We used some general integration rules, arithmetic rules, and product rule for derivatives. And these are all based on many, many other theorems, all built on top of each other. And we depend on those working properly all the time. In fact, people take it for granted that these theorems are always going to work because they've been proven and built on other things. Again, because God has designed all this in. If humans had created mathematics, there's no way that humans could have figured out all the intricate interconnections and how a person might do these theorems in different ways at different times. But because God designed it, it all works. Like, for example, if we couldn't count these working, we'd have to derive every rule every time we did an integral. That'd be impossible. It'd take us weeks to do one integral. We might have to reprogram our calculator every time to find an integral. Now let's take a look at what's called Fermat's Christmas theorem. On December 25th, 1640, Fermat made the following conjecture. A prime number p may be expressed as the sum of two squares, like this p equal x squared plus y squared, if and only if the prime number p can be written as 4 times n plus 1 for some positive integer. In other words, you can write a prime number as a sum of squares as long as a prime number is of the form 4n plus 1. And like, for example, you could take 17. Notice 17 is of the form 4n plus 1 because if you substitute n equal 4, 4 times 4 plus 1 is 17. And so it's of that form. And actually, 17 can be written as a sum of two squares, 1 squared plus 4 squared. Another example, 29 is of the form 4n plus 1 because you can write 4 times 7 plus 1 is 29. In other words, it's of that form where n is equal to 7. And it also can be written as a sum of squares. 29 is 2 squared plus 5 squared. Now, Fermat was not able to prove his conjecture, but showed that it worked for all the numbers that he could find, all the numbers he could try. So now someone did finally prove it in the 1750s. Euler produced a very complicated proof based on finite descent. That actually, Euler did that. Then About 20 years later, Lagrange gave a proof of the theorem based on quadratic forms, a completely different proof. Then later, a proof was given using complex numbers of the form n times I plus m, where m and n are both integers. Again, I is, of course, the square root of -1. Now, of course, you say, what does complex numbers have to do with this at all? Now, of course, it turns out that complex numbers are often used in number theory, but again, it doesn't look like there's any connection. And certainly, this third proof is completely different than the first two proofs. Then another proof was produced based on convex sets. And so convex sets, like here's an example of a convex set. Like a convex set is a set in which you can pick any 2 points in the set and connect the points with a straight line, and the whole line will stay within the set. For example, you can see this set here. If you pick the point here and a point here, you could draw a straight line. The whole line would stay within the set. No matter what 2 points you pick within the set, you could always make a straight line between the points, and that line would stay in the set. Now, you can see this one is not convex because you can pick a point here and here and connect a straight line. A straight line will go outside. Same thing here. Pick a point here, and connect the line will go outside. But on a triangle, it's convex because you can pick any point here and any other point and draw a straight line between the points, and the whole line will stay within the set. So that's a convex set. So again, this proof was based on convex sets. Again, what does that have to do with the original theorem that we had? So look at all these proofs here. They're all completely different, all based on different theorems, and they don't in no way related. In fact, it's hard to even see how there is a relationship between what's the complex numbers and the theorem, or convex sets in the theorem. And then in 1990, Don Segui proved the theorem using basic algebra, a completely different proof, using different area of mathematics. Then finally, a proof has been constructed using partitions. Partitions, I think they use the kind of partition you might use in abstract algebra. But if you look at all these, there's at least 6 different proofs from completely different areas of mathematics using completely different theorems, and they're all were able to be used to prove Fermat's original conjecture, which was of this form. Again, some of the proofs, it's hard to even imagine how they're related to this. But again, it really shows how math has been designed and how God has designed all these intricate things into math. And then you can prove things in many different ways because the math is all interconnected and has all been designed by God. Now, God has built other amazing relationships into mathematics. And let's consider a differential equation. There are many differential methods to solve differential equations. If you've had a class in differential equations, some can only be solved by one particular method. Some can be solved by different methods. Some equations can't be solved at all. Now, mathematicians discovered what's called the Laplace transform, and they've discovered many theorems related to this. This function really has nothing to do with differential equations, but someone decided to use theorems to relate Laplace transforms and apply them to differential equations. So this person tried to see if they could prove theorems and prove things related. And so they followed the theorems, they followed all the rules, and they came up with this. So for example, you could solve differential equations again by separation of variables, exact methods, variation of parameters. But with Laplace transform, you do it a completely different way. We start with a differential equation, and we use the Laplace transform to convert our ordinary differential equation into an algebraic equation. Then we solve the algebraic equation and then use the inverse Laplace transform to get back to the solution to the ordinary differential equation. In other words, instead of going down vertically from the ordinary differential equation to its solution, we transform it to the algebraic equation, solve that, and then convert it back to an ordinary differential equation. Now, this would be impossible unless the mathematics underlying this and was designed and everything worked together, because it makes no sense that you could transform into an algebraic equation, solve that, and then transform back the solution of a differential equation. Again, many solutions to many differential equations could be solved by this. No one has to check to be sure solutions are correct. Long as the theorems were applied properly, you'll get the right answer. And you could even go one step farther to partial differential equations. Once again, there are many methods to solve partial differential equations. Some partial differential equations can be solved with only one particular method, some with many. Some cannot be solved at all. Once again, you can apply Laplace transforms to partial differential equations. You can apply them to partial differential equations and get an ordinary differential equation, solve that, and use the inverse Laplace transform to get back to partial differential equations. And then if you, in certain cases, you could apply Laplace transform to the ordinary differential equations in the intermediate step to solve that. So all these intricate interrelationships had to be built in. They had to be designed in the mathematics by God. It is no way you could figure this out or anticipate all these interconnections. And going to calculus, there's something called a Green's theorem that relates the integral around a closed curve to a double integral over the enclosed area of the curve. And this also is an amazing theorem, because what does the line integral around the outside of a curve have to do with the double integral over the area inside? But it's an amazing theorem, again, called Green's theorem. I have a kind of fuzzy here, so let me just show it real quick. And again, this is an amazing theorem that people have discovered, and it was built into math by God. And the divergence theorem, also a similar idea. Instead of doing a surface integral over a surface, you can do a triple integral over the volume enclosed by the surface. And that's this theorem here. And so you could reduce very difficult integrals, let's say this one here, which is super hard, and use one of these theorems, use, say, the divergence theorem, and you can solve it very, very easily. I won't spend too much time on this, but again, these are just amazing relationships God has built into the universe. And how can these theorems work? And then there's also Stokes' theorem, which has a similar relationship. How do these work? Again, God designed the principles and theorems in mathematics. Humans only discover and apply them. Humans can name and format them. God has designed some amazing relationships in the mathematics. And for by him, Jesus, all things were created, both in the heavens and on the earth. He is before all things, and in him all things hold together. Even mathematics, he has created them in such a way, and he sustains these, and he sustains them for us to use. And all things came into being through Jesus, and apart from him, nothing came into being that has come into being. He was in the world, and the world was made through him.